Good afternoon, everyone. Welcome to IME 765 machine learning class. Today is April 27th. First, as usual, let me stop the video and share my screen. Here we go. Okay. So in the last class, we've mentioned in the last we've mentioned the best selection, subset selection, okay, regarding the model itself and how to make it to MIQP formulations. And also we've mentioned the backward stepwise selection. This is actually what? This is actually the same as we mentioned before, no matter in lecture 9 or in the logistic regression. Remember it. What we're going to do is that if it's just for a single variable, we're going to just run the t or z test and drop the lowest one. I'm going to keep dropping until I have k columns inside. By the way, here I said k columns inside means for x columns corresponding to the bj. Okay, the same. And in some cases, if I want to consider some variables as a category, as a group simultaneously, so that I can use the f-test. First of all, f-test when the group size is 1, meaning that only one variable in the group. So it can be proved that f-test, this one's going to be the square of the score first. And the second thing is that in this case, I can just use the f-test. Why? Because it's more generalized. It can handle the case that there are several variables in one group. Okay, then do the same. I'm gonna run the f-test and keep dropping the one with the smallest f-test score until I have less than or equal to k variables or columns inside. That's the backward. So why it's called backward? Because in the beginning I consider the full model. I consider all the all the p+1 variables, and then I keep dropping until what? Until I have only less than or equal to k variables, and hence it's called backward stepwise. Today we're going to introduce forward-wise stepwise selection. So before it, let's do some review of the math. This part, let me do it quick. One reason is because of the time. The other reason is because you have seen it in the last class. I remember I wrote it in a Word document. Okay, so first part is here. Use the QR factorization, and I can write the beta into this form. So just substitute x equals to qr and do the calculation, and you're going to have this. And the Q matrix has orthonormal columns, okay? So that I must have QTQ equals to I. Again, be very, very careful. If Q is not a square matrix, formally, if it has orthonormal columns and it's square, it's called orthogonal matrix. If Q is not an orthogonal matrix, you do not have QQT equals to I, okay? QQT is another thing. Orthogonal columns, that means QTQ equals to I. Be very careful, okay? Okay, since beta equals to R inverse QTY, so I substitute to the estimation of Y, which is Y hat equals to X beta hat, so that I have this. By the way, if you feel it's too small or you cannot see something very clear, please directly let me know, okay? You may need to unmute yourself, otherwise I may not be able to hear you. And then plugging this one to the RSS formulation, I get this. And then do some math. I just expand it because, the norm of x equals xt times x, right? So this norm I expanded equal to yt times this part of y, and then times this part times y. What I'm talking about is this. And then again, take advantage of orthogonal columns of Q so that I have QTQ, and then combine them, you're going to have this. This and actually is very simple, equal to this, right? So we finally have this thing. Again, be careful. Q is what? Q has orthogonal columns, but QT is not. QT is orthogonal rows, not columns, okay? So you cannot just delete it. Otherwise, something is going to be very, very wrong. Remember what we mentioned before, that in the norm, if I have an orthogonal matrix, I can just delete it, right? But be careful, here's Qt, okay? So you're gonna have Q times Qt instead of Qt times Q, which will not give you an orthogonal, which will not give you an identity matrix. Okay, now have a look at this. What is Qty? Qty is actually what? The coordinate, right? Qty is because Qty equals to this. Where? Oh, I actually wrote it here. Qty equals to inner product of Q and Y. So this means what? This means the coordinate of Y under the new basis. Why new basis? Because all the Q columns are orthogonal. That's why this actually means the the coordinate of Y in the Q basis. Okay, now these are the mathematical kind of like preparations. After having this kind of mathematical preparations, let's see what is exactly the forward stepwise selection. So in terms of the principle, forward stepwise selection is a greedy selection method that each time it selects the column of X that can reduce the residual sum of squares, RSS, the most. So first of all, be careful. This is a heuristic or a greedy selection method, okay? I never claim that the forward stepwise selection method will really give you the best subset selection. Because if this is true, then you have proved P equals to MP. Clearly, it's not. So this is a heuristic method first. And it's very fast. You can see it's really fast. And what we're going to do, in terms of principle, it's greedy. Why greedy? Because, okay, so suppose I have already selected L columns. Then what I'm going to do is that for the columns rest, I'm going to select one which can reduce the RSS the most. You know what I mean? That's why it's a very clear greedy selection method. Okay, to make my life easier, let me use some math notations. First of all, because I usually use xt as what? As kind of the rows, right? Because for example, x1 is the first data. So x1 is actually the first row and the t, first row t. Transpose, so that I'm not going to use X again. This time I'm going to use alpha. Just to let you know, X columns means what? What I mean is this. Let me open the Word to make my life clear. What I mean is this. Okay. So if I have a matrix X, this actually equals to here's some notation things. B matrix, okay. This actually equals to, I'm so stupid. Anyway, this actually equals to this. Here we go. This actually equals to x1, let's say x1t. V dots, and then I have xmt. So these are some notations. In other words, my xi means the transpose of the ith row, okay? The ith row, okay. And to make my life easier, now I need to define the columns. And so I use it in this way, alpha 1. So alphas are the columns of the matrix X. Alpha P plus 1, okay. Let me see, in my notes, did I use alpha 0? I forgot. Okay, so here, I use the S1, SL minus 1. That means that the one that we have already selected. Let me make my notation to be in this way. Let's say, let me start from alpha 0, so that here I don't need P plus 1. I only need P, which makes my life easier. Okay. So among all this, let me see, the feature space should be what? The feature space should be, yes, feature space is 0, 1, 2, 3, 4, 2P. Okay. By the way, I have to mention that in some cases, people do not consider to drop intercept 0. So in some cases, the best subset selection, and later you're going to see Lasso and the ridge the same, we're not going to drop 0. We are going to drop 1 to P. And this is just some, small things, not a big deal. And you can see that with a shift, this will not be a problem. I will introduce it in the region Lasso. So here, let's assume that my alpha space is alpha 0 to alpha t, P, okay? Now, suppose I have already selected L-1 columns. So, and I call it to be alpha S1, alpha blah, 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 and alpha SL-1. Okay, now, by the way, guys, is it big enough? Can you see it clearly? It may be too small. Maybe I'm old. Now it's big enough. Okay, so suppose I have already had this. I have already done in the previous, let's say, L-1 steps. I want to determine the Lth step, the selection of the column in the Lth step. Now, the QR factorization, the thin QR factorization gives me this, suppose. Okay, suppose, again, because I'm running the Lth step. In other words, all these kind of things, this kind of like alpha S1 to alpha SL-1, and also this kind of Q tilde and R tilde R L-1, all of them I've already known it. Okay, now see the idea again. It selects the column of the remaining column of the X that can reduce the RSS the most. Okay, now let's have a look. The current RSS is what? My current RSS, because I have already had this Q tilde L-1 and R tilde L-1, right? So this equals to this. Jesus, okay, whatever, clear all. Because of this one, this formulation, see here, this is the RSS formulation. I plug in inside where this Q is actually the Q tilde L-1. Okay, I'll plug it inside and I get this. This is the formulation of my RSS L-1. Again, by the way, this is already fixed. Nothing to select. This is just, to show you the fact. Okay, now suppose I've already had this. I want to choose the Lth column. Let's call it SL. And I want to find what SL is. Okay, now again, use the same formula. I should have RSSL equal to the norm of Y minus Q tilde LTY, right? And Q tilde LTY should be this. Q1 tilde inner product. This is gonna be, wait 1 minute. Yes. This is gonna be the first element. Get a point? Have any questions here? What I'm talking about this. Let me direct it right here. Q tilde LY. This equals to, okay, anyway, give it up. This is too difficult for me to write it. Let me directly use a word. Word is easier for me. And this is the thing that I really dislike for the online thing. It's so slow. It's here. So I will have QLTY, right? QLTY equals to what? Equals to Q tilde, sorry. Q tilde TY. Okay, so this equals to tilde Q1 3 dots tilde Q L-1. Sorry, L actually, but I do need this L-1 because I need to show you something. Here, this one times what? Times Y, right? Times Y. And this equals to what? This equals to simply a matrix. The first element is what? The first element, oh, give me 1 second. Oh, T. Otherwise, it's wrong. Let me see. No, it's wrong. Give me 1 second. Sorry. There's something wrong here. It should be in this way. T. This is also a T. and this one times y. And this one times y is very simple, which is what? Which is, by the block matrix, y v dots, and then ql y. Okay, and hence, because this q tilde 1 ty is what? Is the inner product of q1 y, right? And the same until I have what? Until I have ql y. See here? And that's the reason why we can write it in this way, okay? But why do I need to write it in this way? Because I want to show this. See here, I've already had RSS1, RSSL minus 1 equal to this. So if I have this one, that means what? That means this equals to RSSL minus 1 minus the new added item. See it? Which is the square, because I have a 2 norm, a square of the 2 norm, which is the square of the inner product of the new selected column QL times y. By the way, so this QL tilde is corresponding to the SL, okay? So in terms of X, the index is gonna be X SL. In terms of Q, to save my life, I directly write it as Q tilde L instead of Q SL. It's gonna be very confusing because, Ara, are you looking at the class? I saw you have a very beautiful smile. Anyway, because if I use the QSL, then it's going to be something different, because you can get confused about the notation, about the notation of what? The notation of the original QR decomposition. Be very careful once you choose different columns or change the orders. The QR decomposition is going to be different. Be very careful. That's the reason why I need to add a tilde here instead of directly called, let's say, QS1 or QS2. You know what I mean? The QS1 will be completely different from the Q1. Why? Because you have already selected the columns and you have already removed the columns. It's going to be very different. Be careful about that. Okay. And now, okay, I think I wrote it here. See, be careful that this one going to be very different from this. Be careful about this. Okay. Now what we're gonna do is that in order to make this one the minimum, because this is the idea, reduce the minimum, I must have what? I must choose the L such that this QL tilde L inner product of y is the maximum. Then how to make this one to be the maximum? So what we need to see is this. First of all, I have this. We will choose this one is the maximum of this part. Then how do we calculate the Q tilde L? Remember it? We use Gram-Schmidt method, or you can say modified Gram-Schmidt. No difference. You can use either one because the principle of them are exactly the same. The only difference is to change the order of calculation. Without the loss of generality, I choose the traditional or the classic Gram-Schmidt process. Okay. Now let's have a look. In the traditional or classic Gram-Schmidt method, we have what? Q tilde L equals to this. This is from directly I copy and paste from the formula here. This is lecture 9. QR factorization. Where's my QR factorization? QR factorization. It's here. Okay. You can see this one and this one the same. I just copy and paste. Of course, I added some tilde, some notation things, and then this equals to this. All these are just some basic notation things. Now I'm gonna make this one to be the maximum. In other words, I need to choose the L column such that this one is the maximum. See it? Okay. Interesting thing is that, in many textbooks, including our great text, this one, including our great textbook, all of them just. No, I think our great textbook even didn't write anything here. I think it's an exercise or something. I forgot. This part, if you look at most this kind of machine learning or statistical books, this is the final result. And I don't. First of all, it's correct. Of course, no problem. It's correct. But the personal one, I feel it's not beautiful enough. So I did something more. And an interesting thing, I found something really interesting, surprising things. And the following, I don't know whether you have seen before, but at least I've never seen before. As something I made it by myself. Okay, so after, and of course, for choosing the first column, we just, for any L as in F, because I haven't choose anyone, I want to make, this part to be the maximum, because of course, you don't have any Q here, you know what I mean? So simply, you can just ignore, you can just delete the Qs here, the Q items here, and then you're gonna get exactly the same formula as here. This is for S1, to choose the first column, okay? So in many textbooks or class notes, in almost all of them, they stop here. That's it. And in the following, I'm going to show you that this one can be further simplified and make a more beautiful formula. Okay, let's see how to do it. First of all, I continue with the numerator, and let's see. So the numerator here is this, and I just plug, just the multiplication inside. So this is the norm. Inside is the inner product of this and this, and I expand again. ALQ, the inner product equals to alpha LT QI, and this one is, I reverse it to be QIT and Y, because ATB equals to BTA, no difference because that's a number. Okay, then if that the case, I can take the ALT out, because this summation is for I. So I only have this part inside, sigma QR tilde and the QRT. And then this part is what? It's actually this part. This is very easy to be recognized, okay? You need some time, however, to think about it. By the way, Mahabuba, still remember how to write this part? You should have 3 methods to write it. That's the thing I taught you yesterday. No, not yesterday, sorry, last year. You should have 3 methods to write it. Way number 1, use single value decomposition. Way number 2, use the AX. Way number 3, use the matrix, rank 1 matrix generation. All 3 methods gonna give you the same idea. I hope you still remember it. Okay, so after it, we're gonna have what? We're gonna have this one, right? And this one actually equals to this one. Why? Because I have a formulation before to estimate the Y star, the Y hat, which is, let me see where it is. It's here, okay. So I have what? I have Y hat equals to QQTY. In other words, Y equals to what? Y equals to the inverse of QQT times Y here, you know what I mean? So you just put this part, take this part, and then make an inverse. Make this one here and inverse it, okay? Then you substitute this part inside here, you have what? Y equals to QQT inverse of Y hat, okay? Now you have this, QQT inverse of Y hat. See it? They cancel each other. So this simply becomes alpha LT and Y hat L minus 1, which is nothing but the inner product of alpha L and Y hat L minus 1. And this finally, further thing is, this is the basic things about the inner product, and I get this one. I'm very happy to get it, to be honest, because this one purely I got it by myself. Okay, then how about the denominator? And the truth is, yes, the denominator can be somewhat simplified as well, using exactly the same thing. The denominator is just here. You don't have a YT anymore. So I use exactly the same method, do this, and then write this one to the QQT alpha. And then this QQT and alpha alpha together, I can take it out, which is what? Which is an, I matrix. And then I do further things because I don't have a square here. So I have to have add a square root here of this. And again, use the trick, which is this one times this one is itself, okay? Then I get this. And then, by the way, here I and also QL minus 1, QL minus 1T, both of them are what? Are symmetric. Now I have this. And then after one step simplification, I have this. So finally, 15 is equivalent to this, 219. Looks nice. It's much easier than this one, see it? Although, to be honest, in terms of calculation, the same, because no matter what, you have to use this way to get the Q. But it looks, it's more beautiful mathematically. And you know what? This has a stronger interpretation. Why? Because some of you may have seen this method. This method is known as the LARS, actually. Least angle, what is the name? Least angle regression. I don't know, like Arab, have you heard about it? No? In regression class, they've never introduced this one? Interesting. I feel that my class, this class, machine learning class about the regression part is deeper than your regression class. Well, anyway, so because this is a basic method in the LARS, that every time I'm going to calculate the projection of the R equal to Y minus the current one, see it? And this is use the residual vector R. And then I'm going to choose the column, X column, which, sorry, where it is? I'm going to choose the X column, which gives you the most, which is the most parallel to this. That means that if I include this one, I'm gonna reduce the most. What I mean is this. Let me open the lecture here. Let me take advantage of this picture. Okay, so I have, for example, suppose this is YL minus 1. And I have so many different columns. I'm gonna choose the column that is the most parallel to this. Because I included this part, then I can make a reduction of this part. You know what I mean? And this part reduction gonna be the maximized. And hence I'm gonna write the formulation of this way, okay? The interpretation again is because of what? Is because I want to choose the column L, which is the most parallel with the Y minus YL minus 1 hat. YL minus 1 hat means currently I've already selected L minus 1 columns. Using these columns to estimate and the residue here. This is the current residue. I'm gonna find the column which is the most parallel to the current residue. That means what? That means the projection of this the projection of this column onto my residue gonna be the maximum. And hence, if I include it, I'm gonna reduce it the most. Again, it's heuristic. It's heuristic, and divided by this part, the X column itself. Because be careful, here X column is no longer normalized, and X column can be very, very large. And I choosing this way. And the interesting thing is, again, in many books, even some very famous, let's say, researchers, they may thought these two are the same. And the proof is already here. They are not the same. See here? However, indeed, the ideas are the same, but they have a very small difference, which is here. See it? Okay, so in many lectures, or actually in most applications, you can either use this one, claim this one to be the forward stepwise selection, or this one is more accurate, because this one really uses the pure idea. The original idea that each time I select the column of X, that reduce the residual that reduce the RSS the most among the remaining columns. So this one is more accurate than this one. However, you have to admit this one is much easier. Why? Because I don't need to calculate the QRT composition here. You see it? I just directly use the column. I'm done. Here you need to do the QRT composition. However, usually QRT composition is really fast. You know, so it's not a really big thing unless your X is really huge. If your X is huge, maybe you can, you know, do it this way, because it's a faster. Simply because it's a faster. You don't need to do the QRT decomposition here, because you have a Q L minus 1 T hat here. So you need a tilde here. This is tilde. So you need to do a QRT decomposition. Okay, and this concludes the what? The forward where it is, the forward stepwise selection. Any questions here? By the way, be careful about this. Due to the time limit, you do need to read the slides, read the lecture notes very carefully after the class. I know it's almost impossible, you know, in just about 30 minutes, you've already understood everything and you can rewrite everything. No way, unless you're a genius. Again, very important things for you guys is do not just read it. You read it today, it's still mine, not yours. Tomorrow you're gonna forget it. What you need to do is try to read it and then take your pieces of paper, or you can open a LaTeX file, or let's say Word file, whatever, write it by yourself. Do you understand? One day you can write it purely by your language, And if you're lucky, you can find some of my mistakes or some better conclusion, for example, like what I did here. Congratulations, it's yours. That's the most important thing, okay? So if no question here, let's go to lecture 11. Okay, so in lecture 10 here, we've already mentioned the meaning or the motivation of sparse regression. And basically, we have already introduced the BSS, the best subset selection. And strictly, this is not a shrinkage method because there's no shrinkage here. This later you're gonna see this is called hard thresholding. That I just drop, hardly very, what should I say? I just give a hard thresholding and then drop the variables. And in lecture 11, we're gonna introduce ridge and lasso regressions, which actually includes shrinkage items. For Arab, have you heard ridge and lasso regression before? Yes? Hello? Can you hear me? Oh, you need to unmute yourself. Have you heard about it before?
Yeah.
No matter in your research or in your other classes. Okay, very good. Let me ask you a question. What are the applications of lasso and ridge regression? Did you learn it in the class or in your research project or something else?
In class, actually.
In the class? Okay, very good. So, okay, but anyway, let me start from the beginning. I assume that you have never seen ridge and lasso. Both of them are shrinkage method. Both of them give a regularization part. When I say regularization part on beta means that I'm gonna have a penalty on the norms of beta. So first, let's start with the ridge regression. For the ridge regression, the original formulation is in this way. Okay, if I remember correctly, ridge regression was proposed very firstly in 1970, maybe around 1970. And the very original meaning is to handle the case that XTX is not invertible. And let's have a look at why it is true. Okay, first of all, this is the original model of ridge regression. Be careful about one thing, which is that here I have a beta 0, right? And my beta is in p plus 1, meaning that from beta 0 to beta p, I totally have p plus 1 betas. But have a look at here. J is from 1. See it? In other words, I'm not gonna add a penalty on the intercept, beta 0. Okay, and later you're gonna see because of this, we need to shift it and then reformulate it. But let's have a look at the motivation. An equivalent Lagrange form is this. You can just put this one here and then make an equivalent Lagrange form. And you may say, hey, why they're equivalent? As we know, usually Lagrange form for this one is a lower bound, right? Because any feasible solution here is a feasible solution here. So it should be a lower bound. Why you say equivalent? And the other thing is, where's the t? The reason I said equivalent is because if you write the KKT conditions of this one and then compare it with this form, sorry, if you write the optimality condition of this one, and then you write the KKT condition of this one, and you compare these two, you're gonna have a 1-to-1 mapping between the t and the lambda, and hence they're equivalent. Of course, an easier way to save your life is say, okay, Slatter's condition done. Which, but Slatter's condition requires a bit more background about convex programming, so it might be a bit more difficult for some of you. And if you're interested, just search Slatter's condition, and you're gonna see what it is. A very good textbook to recommend you is this one. Oh, you're so happy. Let me see. Where's my video here? Okay, is this one convex optimization? You just search it and you can download it for free. Okay, so convex. What's the name? Convex optimization. I call it Blue Book. So that's it. And here, so by adding this one, what we're gonna have is that we have this item because they're equivalent. So let's have a look at this one. And the lambda here is a user-defined parameter. This controls the shrinkage level. Very clear. If the lambda is very large, what's going to happen? That means I try to shrink it, right? I try to make the betas to be the norm of the betas to be small, so that this part of the total part will be minimized. If lambda is very small, let's say lambda equal to 0, so this model is going to be the same as an ordinary least square model or OLS model, right? So the bigger the lambda is, the more regularized beta will be, or in other words, the more penalty it's going to be if beta's norm is large. Okay, and why we said that the ridge regression can handle the thing, for example, when let's say xtx is not invertible. Think about it. Why xtx is not invertible? Main reason is it's not full rank, right? As we have proved in previous classes, if it's a full rank, then this part must be what? Must be positive definite, and hence it must be invertible. In other words, this is if and only if, okay, not a one direction if. Now, if some columns are dependent, then of course, your X doesn't have full rank, and hence this one does not exist. So why, by imposing such a thing, this gonna kind of like relieve this situation? The meaning is that suppose I have something in this way, then I will have what? Then I will have many such columns to be 0. For example, let's assume, for example, x1 equal, let's say the first column equals to, for example, the second column plus the third column. So clearly they're dependent, and suppose only 3 columns, and hence your rank is only 2, right? Okay, and of course, in this case, your xtx is not invertible. However, if you have a lambda, and suppose your lambda, has a good size, a very, very decent size here, what you're going to have is that you're going to have, for example, beta 1 to be 0. In this case, what's going to happen is that even if your x1 is invertible, your x1 is dependent with your x2 and x3, but because my beta 1 is 0, which means your x1 is going to be removed. Get the point here? So that in this case, for the true x remaining x, which is your column 2 and column 3, this part gonna be invertible. Clear? Of course, this is a very heuristic idea. In the true ridge, I cannot claim this. Why? Because the ridge regression conclusion usually gives you, for example, as what I said, that example, the beta 1 usually is still not really 0. The beta 1 will be something from a very small number. So it's not completely kind of like this one is invertible, but this situation can be eased, which means this situation can be improved. And this is also the original idea for how to read this name, Tikhonov, a Russian mathematician. That also the original purpose for him to propose the ridge regression. Is actually to handle this problem by adding this regularization part here. Okay, then remember, as we just mentioned, that here the penalty part, the j starts from 1, and here the same. But the real beta is p plus 1 dimension, the vector. Then if that is the case, you can not simply write this part to be the norm of beta, or let's say a compact way. Remember, usually what we write in this way, we write it usually in this way, right? We usually write it in this, y minus x, beta, let me use b, 2, right? And for the second part, it looks like, let's say lambda and norm beta, 2. However, this is wrong. Why? Because the first part is, of course, correct. But have a look at your second part. You don't have a beta 0. Be careful that your beta is RP p plus 1, not RP. So that if you want to write the norm of beta, 2 norm of beta square, you must include this beta 0. So there's something wrong. Okay, then the question is there a way we can write it as in a compact way, like a matrix form, make it more beautiful. And not only more beautiful, later we're gonna see a lot of important mathematical properties about it. The truth is, yes, we can write it, but we need some math tricks here. Let me see. Okay, let's, what are these? Let's continue. Okay. So first of all, let's observe this. For each row, I have yi equals to beta 0 plus j for summation j from 1 to p beta j xij, right? Okay. Now I sum all these I rows, I have this. And finally gives me beta 0 equals to y bar minus summation of this and xj bar beta j, where y bar is the average of the mean of the y's, and xj bar means the value, the mean of the input value of the jth column. Okay, now I substitute this 3c into 2. Where's 2? Oops. Smaller. Okay, I substitute this part into this formulation. Then you're gonna see what? You're gonna see, okay, beta 0 equals to this. So I plug in beta 0 to be this part minus this. And then by combining items, I will have this part. I will have this equation. And this equation is what? This equation can be immediately written in this way. See it? Here I changed my parameters. I define y tilde to be y minus y bar, and x tilde to be x minus, I should say xij tilde equal to xij minus xj bar. And actually, see what I'm doing here? I'm shifting it. See it? I've shifted y to, to be the centered, and I also shifted the x to be centered. Or you can say I centered the y and the x. Okay, now after this shifting, indeed, I can write it in this way. And these problems are equivalent. Why? Because in a real application, what you care is beta. Who cares about your, let's say, whether it's y or y tilde or y bar, whatever, who cares? What you need is the beta, right? And by this way, it's very clear. The beta is still the beta here from 1 to p. Beta 1 equals to beta 1p. The beta 1 here equals to the beta 1 here. Beta p here equals to the beta p here. But how would I calculate the beta 0? Because in this formulation, I do not have beta 0. Why? Because of this. Here, I sum j from 1 to p. See it? Beta 0 is gone. Why? Because I substitute beta 0 by this. I substitute this one here. This one's here. This one's gone. And this part is the beta j. Sorry, the beta 0 item here, right? And then how would you calculate a beta 0? Simple. In this system, I actually only need beta 0 equal to y bar. Why? Have a look at this formulation. Have a look at this formulation. See it? This is the beta 0 item. And this is the beta item. So by shifting it, I can claim this is the beta 0. So I estimate the beta 0 by y bar. And then in this new system, which means the y tilde I and x tilde ij system, I can write the rigid problem to be this way, or this way, the equivalent Lagrange form. See it? Okay, and then to make my life simpler, in the remaining part of the whole lecture here, I'm going to use this notation, okay?
Yeah, I have one question.
Yes.
When we determine the beta, instead of beta bar, all other beta, like beta 1 to beta p, then can we determine the beta not from 3c?
Not from what?
5? From
not from
3c.
5?
Equation number 3c.
3c.
Because we have x, we know beta.
You know x, you know beta, you said, right?
Yeah.
Same. It's going to be the same.
Okay, 3c and 5 same.
3c and 5, yes, they're going to be the same. Why? Have a look at this. Have a look at this. The reason is because it's already shifted. Have a look at this item. Be careful here. I do here, the x here is the x minus x bar here. You know what I mean? So they're
Yeah.
going to be canceled. I mean, if you want to do it, you can do it, but it's going to be the same.
Yeah.
Why? Because they're canceled here.
Yeah, makes sense.
Yeah. Okay. Any other questions? No? Okay. So to make my life easier, in the following, everything I define going to be in this way. And your x going to be what? Going to be have only p columns. Okay. Remember in lecture 10 and the lecture 9, what did we say? We say that x has p plus 1 columns, right? The first column of x is 1, 1, 1, 1, 1, right? And here, in this case, my x is pure the input matrix. There's no first column to be 1, 1, 1, 1 anymore. And your beta gonna be also p in RP. In other words, your beta starts from beta 1 to beta p. There's no beta 0 anymore. Okay? And beta 0 is estimated in this way. The reason, as Arapa just asked, because they can cancel each other. Okay? And hence, later when I say the rigid regression model, I mean this model. Okay? Either this one or this one. They're Lagrange form. They're equivalent. And this is also the notation in many textbooks that you can see. However, many of them, I don't know why, they just simply write it in this way without explaining this. And actually, this part, in my personal view, is important. So I added this part in my lectures. Okay. Now, if I have this one, isn't my life much, much simpler? I can immediately calculate it. And Arab, I think you know how to calculate this one, right? You don't have to refer to another paper to get a solution, right? You can do it by your hand, right? You know what I mean? Remember your midterm exam? Okay. So for this kind of simple problems, do it by yourself. First, you have 1 time of training, and the second thing is what? Second thing is it's faster. It takes you some time to find a paper, to get the answer, and also you're not gonna have a training. You get it by yourself. You're gonna get everything, much more clear. Okay. Now I can write the normal equations. Normal equation, what I mean is that I differentiate it, get a gradient and then to be 0. This is clearly convex programming, and it's the whole the full objective function is what? The whole objective function is what? It's differentiable. See it? Very clear. It's continuous. Okay. Now I differentiate it and make the gradient to be 0, and I have this, and immediately I have the ridge solution. This is the accurate or analytical ridge solution is here. And compared it with the OLS solution, you see what? One item is created, is added actually, which is this. See it? And that's the point of shrinkage. The point of shrinkage. And remember, in here, we just mentioned that what's the name? Tikhonov proposed that to relieve the problem, of this one, if this one is not invertible, right? Okay, now have a look at it here. I have xtx plus lambda ip. Let me ask you this. What if lambda is a very large number? What's going to happen? Claim, if lambda goes to infinity, this one must be invertible. Can anybody tell me why? Let's say lambda is a huge number. It's let's say a trillion, and all other x's are just, let's say, between 0 and 1, for example. So in this case, it's going to be a huge, huge, huge thing, right? And this one must be invertible. Why? Because this makes the whole matrix close to be an identity matrix. Very good. Yes, it's going to kind of like be an identity matrix. See it? Although it could be dense, let's say there's an ij element, but all ij elements compared with your lambda, your diagonal elements are 0, almost 0. You know what I mean? So it's close to I, identity matrix I, and of course it's invertible. This is reason number 1. Reason it's kind of heuristic. If you want to have a more rigorous proof, use what? Use again the idea of positive definite matrix. Remember how to say, how to judge whether a matrix is a positive definite or not? Principal minus. Remember? That was almost one of the very last class that I remember. I missed my whiteboard. I even remember it's in my right-hand side. The whiteboard in my right-hand side, I wrote it there. And I forgot whom, Arab or Said. One of you asked me, Said asked me a lot of questions about calculating the principal minus about it. And I remember I made a mistake because I confused about the principal, the leading principal minus or principal leading minus. Actually, till now I forgot which one is which. Either it's called the principal leading minus or leading principal minus. What you need to do is, get the main diagonal. In other words, from 1, 1 to kk. Okay, get the determinant of that. If all of them are positive, then it's positive. The matrix is positive definite. For the details, please look at lecture. Which lecture? Lecture 3 or lecture 4 or lecture 2? One of the lectures. It's inside lecture 3, I guess. And if my lambda is huge, what's gonna happen? You're gonna get a huge determinant for all leading principal minus. See it? And hence the matrix must be PD, positive definite, and hence it's invertible. Get a point? That's the reason why when Ridge was proposed, they used this idea. And hence this helps your XTX. Relieve it if it's not, let's say, invertible by adding this very strong item, it's going to be invertible. Of course, you may ask me, hey, so how large the lambda should be? Because the lambda is user defined, right? And that's the reason why I said you can relieve this situation. I didn't say you can solve this situation. You know what I mean? Because who knows what lambda should you choose? In real application, nobody's going to really choose an infinitely large lambda. I may choose a lambda. It may work or may not work. But at least in the sense that the situation gonna be relieved. See it? That's a very principal idea. And this is a mathematical kind of like, this is a mathematical indication of the point here, that by adding this point, our problem can be solved. Okay, and then let's discuss another special case. And this special case is very important in interpretation and the comparisons of Ridge and Lasso later. The special case is that what if the X columns are already orthonormal? If that is the case, what do you have? So first of all, this item is gone. This is I. Gone means it's I. And then you're going to have what? I times, you're going to have this, 1 plus lambda times I, inverse. And then this immediately equal to what? 1 plus lambda in the denominator and xty in the numerator, right? And this actually equals to what? Equals to the OLS estimation divided by 1 plus lambda. Why? Because this part is very clear, the OLS estimation, right? Okay, and here again, you see the shrinkage part. I shrink the OLS estimation by a factor or by a proportion, which is 1 plus lambda. Okay, and this is the Ridge regression. Okay, and let me give it here. And as by the way, any questions here so far? Here I introduced first the math, the idea or the principle or the motivation of Ridge regression, and then I introduced the reformulation, the detailed math tricks, the detailed math, reformulation, and then the solutions given here, which can greatly explain why Ridge. Give me 1 second. Why Ridge is shrinkage? Yes.
Is the small value of lambda is preferable?
Sorry, is what?
Small value or large value of lambda?
Lambda?
Yeah.
Good question. It depends. It depends. Later, I think in recent years, about 10 years, something, some people use some methods to help you choose the lambda, but in most cases, we choose the lambda by cross-validation. Yeah, I just set up a lambda and then I cross the data and then see whether it's good or not, so I choose the lambda. Another thing to choose the lambda here is about the interpretation of the model. If you want the regularization part to be relatively large, you make a relatively large lambda. Otherwise, you make a small lambda. That's the case. But in general, I cannot tell you which one is preferred. Which one is preferred. In some cases, we may prefer a small lambda. In some cases, we may prefer a larger lambda. And it's also user dependent.
When lambda is 0, it's like
the same. When lambda 0,
OLS, right?
the ridge regression
Yeah,
becomes the OLS.
One goal of the using lambda is to avoid like to get the inverse of the XTX matrix, right?
Sure.
So that if we get small value, if we
It's
get the
not going to
inverse
greatly
matrix
improve it. Yes, you are correct.
with the small value, that means we are using the small penalty function.
Yes, and
right?
indeed, here I assume this exists. I assume this one exists. Okay.
Yeah.
However, for if, as you mentioned, if lambda is small, there's no guarantee. It's possible this one still not still does not exist. It's possible.
Okay, if for small value of lambda is this one is exist, then is it small value preferable? Suppose we are considering that for a small value, this one is exist and this one is invertible.
That's a good question. I don't think I can tell you yes or no, because in general, at least I've never seen, let's say in general, we claim this lambda are going to be the bigger the better or the smaller the better if this one already exists. To be honest, I don't know the answer here. But if you want me to ask, using my personal opinion, what I want to say is that it's user defined. Some users just like a large penalty, so that I can have my betas to be small. Some users I don't like a small beta. I want your beta kind of like to be large as long as this one is invertible. Then I may like a small lambda, as you mentioned.
Okay, if lambda is large, that means ridge solution is far away from OLS solution, right?
Yes, relatively further. And in this case, you're going to have more betas close to 0.
Yes.
Yes. So it really depends. A better way to solve this one is actually Lasso. Later you're going to see. Lasso is regularization plus variable selection, or you can say subsets, whatever you call, variable selection.
Okay.
By the way, one thing is that I don't know which version you downloaded. Last night I uploaded a version, and this morning I actually upgraded. Here I added one more section, which is a comparison of the Lasso. And I think maybe after today's lecture, I'm going to add a little bit about escalator, net, the regularization there, which is actually somewhat between Lasso, kind of like a compromise between Lasso and the ridge. And I think for Abdullah and Mahbouba, you've already seen it, right? Elastic net, you two should have seen it. For Arab, I don't know whether you have seen about this part, but I'm going to add a part here. And actually, it can be proved that this part can be returned, again, use some shift, math tricks. This one can be returned as a Lasso problem as well. So, and Lasso is really, really strong. From here, you're going to see why Lasso is so strong and why Tibashani got a big prize because he invented the Lasso. Okay. So, by the way, any questions about the ridge here? No? Okay, now let's have a look at a geometric interpretation of ridge regression. Excuse me. So first of all, suppose this one is the OLS estimation, the beta here. And very clear, suppose I have only 2 dimensions, okay, beta 1 and beta 2. And then this area is a circle, right? This round circle area, or let's say we can call it a disk area, is actually what? Is actually the Lasso, is actually the ridge constraint, which is the norm of beta is less than or equal to 2. A 2 norm of beta is less than or equal to t, right? Okay. Now let's have a look. What is the RSS contour? The RSS contours must be ellipse. Why they must be ellipse? For almost all books or lecture notes, you're just gonna see that we have the elliptical RSS contour, but they never tell you why it is. The reason is because of this. So suppose X is a full rank, of course, and now let's see what is RSS. Because I only have beta 1 and beta 2, so RSS is equal to this, and then you can expand it to be this way. You have this equal to 0. And this is very clear as what? This is an conic equation. And in the conic equation, usually, for example, suppose this is called Q matrix. Let me make it to be so large. Can I make it smaller? Small. Make it small, please. still so large. Anyway, so if this is a Q matrix, if this Q, the determinant is greater than 0, then it's going to be a what? An ellipse. And if this determinant is less than 0, then it's going to be hyperbolic. Okay, and then if it's equal to 0, then it's going to be parabolic. I don't know the English term. What I mean is that if the determinant is 0, is greater than 0, then it's going to be ellipse in this way. If it's greater than 0, then it's going to be in this way. If it's equal to 0, then it's going to be in this way. If it's less than 0, then it's going to be in this way. Okay. I think I added a link about Wikipedia there. Where is it? 1. Okay, what is 1? 1 here. Okay, let's open it. And then you're going to see what I'm talking about. Here we go. Matrix representation of conic sections. So you're going to see something like this way. See it? Exactly the same matrix notation here. Okay, and your A here is actually my what? My Q, XTX matrix here. And you can see AC, B over 2, B over 2 here. And what do we have here? Here we go, this part. Okay. That's called hyperbola, and parabola. Hyperbola is a thing. Hyperbola is like this way. Parabola is like this way, and the ellipse is like this way. Okay, so have a look at here. How about in our case? In our case, what we have is what? What is this? Oh, okay. What we have is my Q as XTX. And XTX determinant, of course, is greater than 0. Why? Because I assume X has 4 rank. And hence, this one is what? This one is an ellipse. Okay? And this tells you it's like this way. Okay, now I've already proved that my contour here is an ellipse. So I can draw it. Clearly, this point means RSS is the smallest one. And then when it's bigger and bigger, RSS is bigger and bigger, right? If I'm gonna solve the OLS, for example, I just solve it here, I'm done. But here is a ridge regression that you need to guarantee that the solution must be inside of this disk. Somewhere the solution should be. Very clear in the contour, in your contour, I'm gonna find the first contour that has a tangent here. And this tangent gonna be the ridge regression solution. See it? And you may ask me, so why you said the first? Because I may have the second one, which so ugly, which is something like this way. You know what I mean? Just assuming this is a ellipse, I cannot tolerate it by myself. So in this, you are gonna have another intersection point, another tangent point here. See it? So the first one, what I mean is that the smaller one, okay? And this is a ridge regression. And here, you can clearly see that I have a shrinkage. See it? Why? Because in the very beginning, look at my beta. My beta is what? My beta is here. Now have a look at my beta. My beta is so small. See it? It shrinks. And that's a point of regularization of a ridge regression and also the shrinkage. Any questions here? Any questions? So I think this is very clear about the interpretation, geometric interpretation of the ridge regression, right? Okay, now let's have a look. Now let's have a look at the second thing, which is a lasso regression. Lasso regression, the finding of lasso regression, I would say, in 1990s is one of the biggest milestone in the history of statistics. Because lasso regression gives you a very, very powerful weapon that in a relatively small tool, simple tool model, you're gonna solve the two problems simultaneously. That it has both variable selection, which is something like the subset selection problem, and also has the shrinkage, which is like the ridge regression. So let's have a look. The very original lasso regression is this. This is the original lasso regression model. And of course, similar, I have an equivalent Lagrange form which is here. Okay, and of course here lambda is greater than or equal to 0. By the way, Lasso regression was proposed by Robert, sorry, there's a T, Robert, not a Robert, Robert Tiberstrani in 1986. However, in many literatures, you're gonna see two R. Tiberstrani. The second one is Ryan Tiberstrani, who's his son, and he's an associate professor in computer science in Carnegie Mellon. And it's great. I mean, both of them, they contribute greatly in statistics and operations research. Okay, so here I'm talking about the father, the Robert Tiberstrani, who invented the Lasso in 1986. Okay, and similar, we have the problem here because my J is from 1 to P, while my beta is in RP plus 1. So how to handle the beta 0? I'm gonna use exactly the same method here. All the formulation is going to be exactly the same. The only difference is that this beta J is going to be beta J absolute value without a square, and hence this is going to be one norm of beta, okay? And you can write it in this way. And similar, you're going to estimate the beta 0 by y bar. And everything becomes normal, which means I can, becomes compact, I should say. I can use a compact matrix form to write the Lasso as well. And by comparing this one with the ridge regression, what's the difference? The only difference is here, rather than the 2 square, you know, 2 norm square. Okay. By the way, in many other paper, you may see they define the Lasso and the ridge by a factor of 1/2 here. By a factor of 1/2 here, 1/2. Which is added here, you know, in this part before the norm. This is why, because they want to, you know, when they do the different, you know, the gradient, these two can be canceled. Okay, and also for the ridge the same. But essentially, there's no difference. Okay, so how to calculate it? And you might say, okay, easy. Let's do the same. I just differentiate it and then normalize it. Use the normal equation. And, you know, make a lambda, the nabla to be 0 and done. Unfortunately, it's wrong. It doesn't work here. Why? Because this problem, this objective function is not differentiable. Arab, do you know why this one is not differentiable? Abdullah, do you have any idea?
This is not convex.
Who tells you this is not convex?
No, it's convex because, you know, this is like a straight line. You know, this is straight line. The mathematical representation is a straight line. So is this not differentiable? If we differentiate, it becomes 0.
Not exactly. What you are talking about is because you just remember the conclusion. What you are talking about is this. What I'm talking about is this. If that's the case, if this is the case, it's no longer gonna be a diamond. You're talking about a diamond because of this. It's not a diamond at all. It is in this shape. That's why it's not differentiable. Okay.
Yeah. It's straight line. Yeah.
It's not diamond. Diamond because you have less than or equal to t. It's going to be a diamond. But here I'm talking about the Lagrangian form. It's not a diamond. It's in this way. Why not differentiable? Remember, what does the meaning of differentiable? That means the left derivative equal to the right derivative, right? But at this point, 0, beta equal to 0, your left derivative is -1, but your right derivative is +1. They are not the same. And hence, this function is not differentiable. Just consider y equal to absolute value of x. It's not differentiable, right? I believe all of you have learned this in calculus, a very simple thing, right? Okay, now the problem is what? The problem is that it's not differentiable, so you don't have the gradient. So what would you do? It's going to be a problem. What we're going to do here is that, well, although I don't have the gradient, I do have the subgradient. And I can use the KKT, let's forget about KKT. I can use the subgradient optimality, and which is actually the same as the KKT condition, the stationarity, the first condition of the KKT conditions. Due to the time limit, I'm gonna introduce this one, I think, on Wednesday. But that's everything about the ridge regression so far. And after today's class, please do read lecture 10. And then also review the part of lecture 11 about the ridge part. Again, as I mentioned in the beginning, due to time limit, I don't think I can, really show it step by step. However, as I wrote these lecture notes, I think it's going to be very clear. It took me huge amounts of time, I can tell you. Really, almost all the time I just spent on this kind of lecture notes and also some other research topics. And I think as PhD students, it should be not difficult for you to read this. Please carefully read it. And if you have any questions, just let me know, okay? Okay, that's everything about today's class. And Arab, I will see you at, let's say, 4:30. Give me a little time for a short rest, okay? Okay, thank you very much.
Yeah.
Have a good day. Actually, good evening almost. Bye-bye.
Bye.